Okay, morning everyone. Let's get started. So first of all, on Tuesday, 2 days ago, we have our previous TA to give a presentation about how to debug machine learning code, how to leverage NumPy and SciPy libraries. I think that will be very useful if you feel unconfident or uncomfortable in debugging like decision trees, SVMs, or even neural networks later. Also, he has we have shared his slides and lecture video on the course website as well. Like, I will suggest you guys like if you cannot find any clue to debug your code or need some guidance, you can watch his video again. Okay, the second thing is about the homework one, the decision tree learning. If you still haven't started doing that, please do it right now, because you do need some time to make it work on the data sets. Although you might be clear about every detailed step in algorithm table, but when you implement them, you transmit them into Python source code, it will take some time. Okay, and also please feel free to leverage the office hours, especially on Friday. We got, I think, 4 or 5 hours. Right? So if you do have any problem, just please stop by and ask help from a TA. You're also welcome to stop by my office hour. Although I still feel like my office hour is pretty empty so far. Okay, so prior to the machine learning debugging topic, we talked about the very fundamental concepts in computational learning theory, right? So we talk about definition about the generalization error, the definition about empirical error, and we use a very simple example, like assuming that your hypothesis space is finite and you have a very strong consistent learner. By consistency, we mean like whatever training example set you give your learning algorithm, it always find you a hypothesis which gives 100% prediction accuracy on the training set. Right? Based on that ideal setting, we show that we still have some chance to return a hypothesis whose generalization performance is not good. Right? If you can recall that kind of lengthy statement, right? With the probability at least 1 minus delta, you find a consistent hypothesis to the training set, yet the true error is bigger than epsilon. What's that probability, right? What's the bound of that probability? If you want to control that probability to be some designated level, how many training examples do we need, right? That's the first sample complexity bound we introduced in our class, right? The major motivation is to tell you how useful this computational learning theory can help us to build the sense how the training data size relate to the generalization error, right? And also through the bound, we can see some insight about or justification about the Occam's razor's principle, right? So later, when we talk about infinite hypothesis space, meaning that your hypothesis space contains infinite many possible hypotheses, right? So how can we characterize the sample complexity bound, right? Through that bound, we can derive a new learning principle, which is called large margin classifier, right? And based on large margin classifier, we can introduce, or we're motivated to introduce the support vector machines, right? That's the whole idea, right? But before that, right, we want to continue our discussion about decision trees. Actually, based on decision trees, we're going to introduce a type of even more powerful machine learning algorithms, which is called ensemble learning. right? So does ensemble mean, right? So literally, it means that you got a bunch of different classifiers or learners, right? You use some smart way to combine them together, and assemble them into one more stronger classifiers. So we're gonna introduce two classical ensemble learning strategies. One is called boosting, the other is called bagging, right? So boosting, you will see later today, is to assemble a set of very weak classifiers, right? So you can view it as, okay, I got a set of junkies, but I can convert them into a very powerful, very stronger algorithm. This is called boosting. And bagging, on the other hand, they try to build a single classifiers to be as powerful as possible. By powerful, I mean you want your classifiers so strong to overfit the training data. However, if you can simply collect them together and make some average over the prediction, you will find surprisingly the overfitting issue can be largely reduced. Yet you're gonna leverage this another advantage, and you'll see that overall their generalization performance will be substantially improved, right? So we'll talk about that in the next step. Okay. So first, let us talk about what is boosting, right? So this is like a type of general machine learning approach, right? So it was motivated by some theoretical study. So here I just want to emphasize that doing research, theoretical research is useful, right? So it arises from the pioneer machine learning researchers who try to answer a theoretical question, right, in the pack learning, right? So they want to ask that, okay, if I have a set of weak learners, a collection of weak learners, right? In theory, you might have like possibly infinite number of weak learners, right? Can we, in theory, guarantee that combining them can give you a strong pack learnable learning algorithm, right? So this paper was written by Robert Shapiro. Like he was a previous professor at Princeton, now at Microsoft Research, right? He's kind of a senior. He was kind of a pioneer in the development of boosting algorithms. Okay. So boosting is a way to create a strong learner using only weak learners, also known as the rules of thumb, right? So it's a typical ensemble method, right? A class of learning algorithms that compose classifiers using other classifiers as building blocks, right? That's what ensemble learning does, right? Boosting has a stronger theoretical guarantees than other ensemble methods. Right? So that means, like in theory, it's very good. And boosting is practically very useful and very widely used. So here we just list a set of typical applications like face detector. Like if you nowadays, like even if you use your iPhone to take the picture, right? You can see that with some people showing up in your camera, there will be some bounding box to bounding the face and so on. Like it's a very common in any like digital cameras. So that requires that you got like very fast and accurate classifier to find the face in the images, right? And dynamically, right? So this is a typical applications from the so-called AdaBoost. AdaBoost is the algorithm we're gonna mainly introduce in our class. And other applications include like handwritten letter recognition, right? If you're given, if you want to send a mail, right? So if you written the address, you post the code, and all those kind of stuff manually, right? So how do you automatically detect those address and the postal code, and then dispatch them into different, mail tracks or transportation path, right? Because some mails are sent by air flights, right? So those are highly automatic automatically nowadays, right? So as this job is mainly done by machine learning algorithms, right? Data boosting is one common use approach, and the other approach is using neural network, right? So if you have done any neural network research, you found that the one very common use data set is to detect the handwritten digits, right? Text classification, news tagging, information retrieval, motion capture, DNA sequence analysis, etc. So those applications are all like examples of successful examples of boosting algorithm. So here we just give a short description about the formal problem setup. Right? This is not required in your exams, right? It's just to give you a sense how they theoretically formulate the boosting problem, right? So in our previous discussion, right, we introduced the concept about pack learnability, right? So we say a learning algorithm can pack learn some type of or some family of target functions if for any distribution over the training or over the instance space, right? For every possible error level epsilon and the confidence level delta, right? And our algorithm can only use a polynomially many random examples to find a hypothesis with high probability, meaning that at least 1 minus delta, to give the true or generalization error less than epsilon, right? That's the definition of the pack algorithm, right? And correspondingly, we have the so-called weak pack algorithm, right? So it used kind of same statement, but the only difference is that we're gonna not require you can achieve the error for any epsilon. Instead, we largely relax the requirement, right? We only ask that, okay, if your algorithm can use a polynomial many training examples to achieve an error of epsilon, which it is slightly better than random guess, right? Because we only require that epsilon is bigger than or equal to half, right? Subtracted by some small number, gamma, right? This is a positive number, right? So the basically means, okay, I just require that your algorithm can find me a hypothesis which is slightly better than you just do some random guess, right? We're doing here, we're assuming we're doing binary classification. So at least your algorithm is effective, right? At least your generalization performance, your accuracy must be bigger than 0.5, right? That means your error must be less than 0.5, right? But we don't require that, okay, your error must be less than 0.01, right? It's just be like, okay, if your algorithm can give the can learn a hypothesis, gives a 0.4, 0.45 kind of generalization error, that'll be fine, right? And such algorithm is called a weak pack algorithm. Then the question in theory was like, does weak learnability lead to strong learnability? That's their initial theoretical question they want to address in the computational learning theory. So here's the brief history about the development of boosting algorithm, right? So to answer that question, right, the can weak pack learners or algorithms lead to strong pack algorithm, right? To answer that question, Robert Shapiro in 1989, he proposed the first provable boosting algorithm, and in his algorithm, it calls weak learners 3 times on 3 modified distributions and applies recursively. So in practice, it shows its first version can slightly boost the accuracy. I mean, in theory, it's good, but in practice, it's bad. Right? And then in 1990, Fruin, this is another pioneer researcher in boosting algorithm development. It showed that the optimal algorithm that should be boosting by majority, right? And then in 1992, they conducted these three researchers, they conducted the first experiments using boosting, and they found that, okay, practically they don't work well. They have a severe practical drawbacks. But in 1995, this is a real groundbreaking development, right? So Froome and Shapiro, they introduced their ADA boost algorithm, right? So they show that, okay, it's not like theoretical well, right? It also shows strong practical advantages over the previous boosting algorithms. So since that on, the boosting starts to become very, very popular and impactful. So this algorithm, ADA boost, was followed by a huge number of papers and practical applications. And Froome and Professor Shapiro, they won a Goldel Prize in 2003, which is the highest award in computational learning theory. Okay, so this is just a brief introduction about how the boosting idea, where it's motivated. Like it starts from the theoretical research, and then how it converted, how it finally be turned into a really practically strong machine learning algorithm. Right. So next, we're going to introduce some detailed algorithm design. Right, we're going to focus on ADA boost. It's the most powerful and the most widely used and popular boosting algorithm. We're gonna start introducing the intuition, and then we gave algorithm steps, and then we briefly explain why does it work. Actually, there's some like open question and interesting observation about behaviors ADA boost we're gonna discuss later. You see that ADA boost algorithm seems like perfect to fit the training data, but doesn't overfit, meaning that it can reduce the training error down to 0, but doesn't overfit. Okay? So it's a very, very interesting phenomenon for ADA boost. Okay. Any questions so far before we proceed to the details about ADA boost algorithm? Everyone's comfortable with the basic idea, the motivation? Okay, perfect. Okay, so again, we're gonna start. We're gonna introduce the details or explain the details based upon a simple example, right? To give us enough intuition. So we're gonna use this example. Right? Our goal is to classify a set of points on a plane, right? So suppose this plane is the domain is bounded by a rectangle, right? We're doing binary classification, so you can see that we have a set of positive training examples and negative training examples, right? And we're going to construct a classifier based upon a set of weak learners, right? So what kind of weak learners do we use? Our weak learners consist of axis parallel lines. That means I either use a line in parallel to the x-axis or horizontal axis, or a line parallel to the vertical axis to construct a weak learner. So you can see this is very weak, right? We cannot change the angle. So as we'll see later, right, we're gonna dynamically adjust the importance weight for every training example according to the performance of the weak learner in each iteration. Right? So at the very beginning, we're gonna assign the same importance weight for every training example. Right? Suppose I got 100 training example, right? That means their importance weight will be assigned as 1/100 at the very beginning. Right? So now let us perform the first step, right? The first step is to find a weak learner, namely one axis parallel line that gives the best prediction accuracy on the training set. Right? And after some algorithm, right, we find that the best classifier will be H1. So you see, it's a vertical line, right? At this position. So now I want to ask, how many mistakes does H1 make? 3, right? We can see that there are 3 positive examples here, which are misclassified by H1, right? And the error, so here we have in total 10 examples, right? If we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we made 3 mistakes, and so our error is 0.3, right? So now we'll proceed to the next step, right? So the key idea of ADA boosting is that, okay, in the next iteration, I'm gonna construct a weak learner, a new weak learner, which try its best to avoid making the same mistake again. Right? So yeah, our first round, while we have to construct a weak learner, we know that, okay, H1 makes mistakes in predicting labels on these 3 examples, right? So in the next stage, we want to construct a new weak learner, but we do not want to make the same mistakes. Right? We're trying to avoid the same mistakes we're making. Right? How can we do that? Yeah. I mean, it depends on your searching algorithm, right? But from the general point of view, right? How can we try to avoid such kind of mistakes? So you want to, can I say again, you want to kick off those examples or?
Those 3 that we know we might get wrong. Make sure it gets correctly classified,
Yeah. We want to make sure that they are not classified. But here there's a subtlety here. Like, you can try your best to avoid misclassifying these 3 examples again, right? But there's not guaranteed, because this is not a strong classifier, it's a weak classifier. This prediction accuracy is just slightly better than random guess. Any other thought? Yeah, that could be another strategy. But here, we want to still like fully utilize the whole data sets information. We do not want to miss any of them, right? Yeah, here is just to motivate us to think about how to fulfill their strategy, right? But their strategy is really straightforward. So in the next round, right, to avoid making the same mistakes, they're gonna promote the importance weight for those mistakes. So previously, as we mentioned, right, all the examples are treated equally, right? They have the same importance weights, right? Next time, right, I want to train a new classifier, right, which is a weight classifier, but I want to avoid making the same mistakes. How can I do that? I'm gonna literally increase the importance weights of these 3 mistakenly classified examples, right? And then it kind of like drive the algorithms try to avoid misclassify these 3 examples again, because it's gonna incur a larger error, right? If you do it, if you fail to classify them correctly again. Right? So that's the idea. So for the next round, we're gonna increase importance of the examples with mistakes. And meanwhile, we're gonna downweight the examples that H1 got correct. So you can see that, because the goal in the next step is trying to avoid the mistakes the previous classifier has made, right? That means, okay, we're gonna lift their importance. But meanwhile, for the other examples, like H1 has already correctly classified, right? We don't need to treat them like that important. So we downweight their importance. So after some like adjustment of the importance weights, we can see that, like, those bigger size of label showing that, okay, they have a larger importance weights, and the smaller size, shrink the size showing that, okay, their important weights are downweight, right? And then on this weighted, reweighted training set, we're going to rerun our learning algorithm, right? And here, we're going to introduce this notation dt to represent the set of weights, importance weights on the training examples at iteration t, right? One for each example, right? Those weights indicate how much should the weak learner care about each example in its choice of the classifier, right? And here we're gonna require that the summation of the importance weight for every training example will be 1, right? It is normalized to be 1. And then after rerunning our weak learning algorithm on this reweighted training set, we get our second weak learner H2. Okay. And we now has the error epsilon2 to be 0.21. Now I'm asked why. Why now the error is down to 0.21? Yes, exactly, right? So here, if we just look at the classification results of H2, right? So H2 is another vertical line, right? We found that it still makes 3 mistakes, right? I misclassified 3 inactive examples, right? But here we need to be careful because all those 3 classifiers, right? The 3 misclassified examples, they downweighted, right? So their weights were decreased. So if you add them up, it will give you 0.21. It's no longer 0.3. Does it make sense? Okay. Why not 0.3? Because while computing error, we will weight each example xi by its weight dti. Okay. Any questions so far? Everyone's comfortable? Okay. So now we'll give the formula to compute this weighted error. So at iteration t or round t, right? If we want to compute the weighted error, we can just follow this formula, right? So you just subtract half by half times a summation, right? Over every training example, right? Inside the summation, we just multiply the sample weight with the ground truth label yi multiplying with your prediction or classification. So here yi is either 1 or -1. And again, your classification result is either 1 or -1. So next, we're going to explain why this is reasonable, right? This is correct. We consider 2 cases. First, if your prediction is wrong, what will happen? If your prediction is wrong, what does this product look like? Yi times HXI. 0? Or any else? I heard someone saying something. What will be the value of this yi times h of xi? Y is the ground truth label, and h of xi is your classification. -1. Like y is -1. Yes, that's a very, very important observation. So just be sure to to keep it in mind, because we're going to use this observation again and again when we discuss other classifiers, right? So if we make a wrong prediction, that means your prediction and the ground truth label disagrees, right? So that means they must their multiplication must be -1, right? Because their sign must be disagree, right? And if you make a correct prediction, what will happen? The product must be 1, right? So imagine that both, if it is a ground truth label is positive, then H and Y will both give positive, right? The product is 1. If they're if the example is negative, then the ground truth label and the prediction must both be negative, and so the product is 1, right? YI, the definition of YI? Y is just the ground truth label. So we're discussing about the binary classification problem. So YI is either 1 or -1. So 1 means that, okay, it's a positive label, -1 means it's negative label. And similarly, your classifier, your learned classifier will also either give positive prediction, +1, or negative prediction, -1. Does that make sense? Any other questions so far? Okay. So now if we take into account these two cases, right? What's the value of this product when you correctly predict example and when you make wrong predictions? So you can show that your error essentially is the summation of the weights for those wrongly predicted examples in your training set. And I will leave it as an exercise for you guys to show the equivalence here. Okay, so now we have a knowing how we're gonna compute the weighted error on the training set after each round of training, right? So, and we have find 2 weight classifiers so far, right? And after each one, we made 3 mistakes. We kind of like promote the importance weights for those examples and demote the importance weights for the remaining examples. Now in the round 2, based on the reweighted training set, we run our weight learning algorithm again, right? We found another 3 mistakes, but their weights, the weighted error will be just 0.21, right? So then, again, we're gonna follow the same procedure. We're gonna increase the importance weights for these 3 misclassified examples. And meanwhile, we're gonna decrease the importance weights for the remaining examples, which H2 can correctly classify. So you can see that after this kind of readjustments of the weights again, here are the new weights. So for the next round, we increase the importance of mistakes and downweight the examples that H2 got correctly. Right? So got H2, right? So, and then based on this reweighted training set, right, we're gonna run our weight learning algorithm the 3rd time. Right? So this time, our best classifier will be a horizontal line. And again, we got some mistakes, right? And sorry, mistakes here and here and here, right? And because of their weights are relatively small, their weighted error actually is just 0.14. Right? So now suppose we have a stop, right? We stop our boosting algorithm, meaning that we have constructed 3 classifiers in 3 iterations, right? We're gonna assemble them into a unified classifier. How can we do that, right? The final hypothesis is a combination of all weight classifiers we have seen so far. So we'll simply do a linear combination. So that means we're gonna multiply the prediction made by H1 by alpha 1 plus prediction made by H2 by alpha 2, prediction made by F3 by alpha 3. Then we have obtained our AdaBoost classifier. Right. So those weights alpha 1, alpha 2, and alpha 3, we can think of them as the weight for each weight classifier. Right. Of course, our boosting algorithm need to specify how we're going to set alpha 1, alpha 2, alpha 3, right? Which we're going to discuss later. But is it clear for everyone the whole procedure? Right. So you can see that we don't need to adjust the weak learner, right? We don't need to change the weak learning algorithm, right? We just need to make sure that your weak learning algorithm can run normally on a set of weighted training data set, right? And then every time we just train our classifier on this data set, then according to its performance on the data set, we readjust the weights of the examples in the training set, right? And rerun the classifier. And again until we finished our iterations. Right? Then we linearly combine all the weight classifiers we have obtained so far and assign some votes for each classifier. That's the whole procedure of the AdaBoost algorithm. Any questions so far? You mean alpha 1, alpha 2, alpha 3? Mm-hmm. Uh-huh. Oh, okay. That doesn't matter. Because these are just showing that those examples are related. But once you got your classifier here, right? What you need to do is that you train a classifier, you make a prediction on your example. That example won't be weighted. You just make prediction and you assign some vote for every prediction. You pick up the one who has larger vote. For example, for a new example, H1, suppose its prediction is negative, right? And the remaining H2 and H3, their predictions are positive, but H1 has a larger vote. Alpha 1 is bigger than the votes of negative prediction, the total votes of negative prediction made by H2 and H3, and then you're gonna still have a positive prediction. This is just to literally show you like how different weight classifiers were trained. Any other question regarding the whole picture? Yeah, we're going to discuss about that details later. But here we just want to show you the general picture, right? Of course, how do you adjust those weights? How do you change them? How do you compute them? Is you might have like a variety of choices. So we're gonna pick up one specific and very popular strategy to introduce. It's very important. Yeah, actually, the critical step is how do you reweight those examples. But I want to say that there's not only one strategy of doing it. Uh-huh. You need some like scheduling. It's I mean, you can do what you want, right? But doesn't give you a guarantee about performance, right? You need to follow some strategy to change the weights automatically and effectively. This one? This one? Okay, so we got 3 mistakes, right? Here and here and here. And their weights are, if it adds up their weights together, it will give you 0.14. And similarly, I mean, this is something we just discussed, right? So for H2, right, you make these 3 mistakes, right? And unfortunately, their weighted error is not 0.3 because their weights are changed. So they are adding up together. I guess that's 0.21, right? In our previous discussion. Yeah. Actually, in every iteration, the weight for every example has already changed. Right? If you want to calculate the weighted error, you have to add up their weights for those mistakenly classified examples. Right? That's why we give this formula, and we mentioned that this is actually the same as you simply add up the weights of those wrongly classified examples. Right? I will ask you guys to show this equivalence. Okay, I hope this toy example can give us a general picture about the boosting algorithm. Any question? Okay, perfect. So now we give some outline, right? We're gonna give some like formal summary of the boosting algorithm, right? So we suppose we're given a training set x1, y1 to xm, ym, right? Suppose we got n training examples, right? And each training instance is labeled with either -1 or 1, meaning that we're mainly doing binary classification problem, right? And we're gonna run our boosting algorithm for big T iterations or T rounds. Right? For each iteration, we're gonna construct a set of sample weights we denote by dt on these m examples, right? Meaning that every training example will be assigned a sample weight. Then based on this weighted set, training set, we find a weak hypothesis HT such that it has a small weighted error epsilon t. Right? And then we're going to reweight our training set, right? We're going to assign a new dt, right, for the next iteration, and then rerun our weak learning algorithm on this data set to get a new weak hypothesis. We continue doing this until we finish big T iterations, and we collect the big T with classifiers, then we construct a final hypothesis H final, right? That's the whole procedure. So then the remaining question is that how do we specify these 2 steps, right? So first, how do we construct the sample weights after at each iteration, right? And second, once we have collected the weight classifiers, how do we combine them together? More specifically, how do we set their weights? Right? So before we introduce AWS, the AWS is one topic, one very popular instance to implement this algorithm. So it has its own way to constructing the sample weights and constructing the final hypothesis. Right? So before we introduce the details of AWS, right, we're gonna just specify the notation. Right? So we use dt to denote the sample weights, right? So dt1 just means the example weight, the weight of the first example in iteration t, and dt2 the weight of the second example in iteration t, dtm the weight of the mth example in iteration t, right? And at every round, the weak learner looks for hypothesis ht that emphasizes example that have a higher dt, meaning that it will those examples with larger weights as more important, right? And trying to avoid mistakenly classify those largely weighted examples. So AdaBoost will initialize the weight for every example to be the same, which is 1 over m. Remember, m is the total number of training examples. So it basically assumes, okay, those examples are respect the uniform distribution, right? And then after t runs, right? And what we have is that, okay, we got dt, right? dt is the weights for the training examples after t iterations are done. And we got hypothesis ht that was learned based on the dt, right? We have also the weighted error epsilon t of that hypothesis ht on the training set. So what we want from the t+1 iteration, right? We want to find a hypothesis so that examples that were incorrect in the previous round are now correctly predicted by the new hypothesis. Okay? How can we do that? We're going to increase the importance of the misclassified examples made by HT, and then decrease the importance of the corrected prediction ones made by HT. Right? How can we do that? AdaBoost use the some kind of exponential factor. Right? For every example I, right? If the prediction made by HT is correct, as we mentioned, right, we're gonna demote the importance weight. How can we do that? We multiply the previous weight, I mean the weight in iteration t, with this exponential factor. So e to the power of minus alpha t. Alpha t here is positive. So you can see that e to the minus alpha t will be less than 1, right? So that means it's kind of like demote the weight. On the other hand, if your prediction is wrong, so that means, okay, you make a mistake, right? So I'm going to multiply the previous weight by e to the power of alpha t. Again, alpha t is positive, so e to the power of alpha t will be bigger than 1. So in this way, it's kind of like amplify the weight. Right? It's not increasing, it's decreasing, right? Yeah, because that's a very interesting connection. Yeah, it's the first time I heard some kind of like this kind of connection. That's very interesting. But yeah, at the beginning, if you will, their weights, you're kind of like assuming their entropy the most, right? Right. And then according to your classifier's performance, you actually change your knowledge about those set of data, right? So you kind of like change the weights, which reflect that you decrease the entropy. I wouldn't say they're gonna convert to some minimum entropy. Yeah, but eventually it's gonna converge to some place like zero training error. But I cannot say it will give you 0. It will give the smallest entropy. But that's a very, very interesting observation. Any other question? Okay. So, and then we got this ZT. Why do we need to multiply? Well, why do we need to divide these guys by ZT? Yes, exactly, right? So this is very, very important. Right? Why do we need this normalization? We just need to ensure that after the update of sample weights, right, we need to make sure their summation to be 1. That's why we need to normalize it. Right? That's how we can compute ZT. So actually, we can summarize these 2 cases together into one formula. That is, we can rewrite our updating rule by multiply the weight in the previous round with this exponential factor, e to the power of minus alpha t times the product between the ground truth label and your prediction. Why is this true? it uses the trick we just discussed, right? So the sign of this product actually reflect if you're correctly predicting that example or not, right? So if sign is positive, right, this means it's 1. So that means you correctly classify the example. So then your factor is e to the power minus RT. You're going to promote the weight, right? Otherwise, it will be negative, -1. The negative will be positive. You actually return to this factor. You actually are promoting the weight, right? And then we multiply this factor, and then we do the normalization, right? How do we compute ZT? Yes, sum up, right? It's very simple. So basically, so here is our unified formula to update, unified rule to update the sample weight, right? So if you want to compute ZT, you first just calculate dt times this exponential factor for every example. And then you sum up them together, you got ZT, right? And it will guarantee that, okay, the summation of all newly updated sample weights will be 1. Just to give you a sense. Okay, any questions so far? Everyone's comfortable? Okay, perfect. So then the remaining question, how do we compute alpha t, right? So alpha t in AdaBoost is chosen as half times logarithm. The fraction, this fraction is 1 minus the weighted error t, epsilon t over epsilon t. So remember, epsilon t is the weighted error, right? It's just the summation of the weights for those wrongly classified examples by HT, right? Now we got this weighted error epsilon t. Now you just calculate this fraction and take logarithm times half, you get alpha t. Right? This is a rule of AdaBoost.
So that's one is you can do it one for all.
Yeah.
Notice that that's one of the question one. So how does that? If you find a negative, why does that decrease the?
Actually, that's why we need to stress that okay, we have a weight classifier. That means to see epsilon t is always less than half. If it's less than half, then this fraction is always bigger than 1.
Oh.
Right. Right. So yeah, if yeah, I mean this is a very important. This is a very good question. So I know in my past experience, and some students came to me complain that, okay, why do I say a negative alpha t, right? That means your weight classifier doesn't work, right? It gives the error bigger than 50%. That's not possible, right? You must have something wrong with your implementation. Right? As long as it's better than the purely random guess, right? That means we require that your error must be less than half. Right? If it is bigger or equal to half, then you got some problem. Is only guaranteed by what? Weight classifiers. I mean, I'm not saying like it's only guaranteed by weight classifiers. I mean, at least a reasonable classifier should guarantee this. Yes. Yes. No. If you want to do 3 class classification, you cannot use this, right? Or you can convert it into 3 binary classification problem, apply that. Otherwise, you have to seek for some extension or some variance of this. Another question? Okay, so this is how we're gonna set this I would say demoting or promoting factor, right? Alpha t. Okay. And this alpha t not only is used in readjusting the sample weights in iteration T. It will also serve as the vote at the final step. The vote for hypothesis HT at the final step. Right? So you can see that alpha T takes two roles. Right? First, we're going to compute the weighted error of your HT after iteration T is done. Right? So you got alpha T. This alpha T is used to update the sample weights, right, to prepare for the next iteration. But this alpha T is also used as the vote for your HT classifier in the final assembling stage. So now we have fulfilled the two steps, right, in this general boosting algorithm, right? So AdaBoost uses rules to construct the distribution of the sample weights in each iteration, right, following this rule, right? At the same time, it constructs the votes of each classifier during the final stage. Right? So now let us take a look at how the final hypothesis or the assembled hypothesis work. Right? So after big T iterations, right, we have big T classifiers, right? H1, H2 to H big T. Right? And meanwhile, according to the weighted error made by each weight classifier, we got big T values of alpha T. Right? And because we're only focused on binary classification problem, right? So each weight classifier takes an example X and produces -1 or +1 as the prediction result. Right? And then if we use final hypothesis to make a prediction for any example X, the prediction will be like this. So you can see that we just do a weighted combination of the predictions made by every weight classifier, and then look at the sign, right? Why? Because HT is either HT of X is either 1 or -1, right? So you add up alpha T times their prediction together, you actually compute the total weights, the total vote, right, for positive prediction, negative prediction, right? If this summation is positive, that means okay, the total vote for positive prediction is bigger than that for negative prediction, right? So we're gonna give we're gonna predict the example to be positive, right? Otherwise, we're gonna predict the example to be negative. Any questions so far? Okay. So now we can look at the full algorithm for AdaBoost. Right? So given the training set x1, y1 to xm, ym, right? M training examples, we're doing binary classification. So each label is either -1 or +1. We got hyperparameter big T. That means how many iterations you want to run, right? That means how many weight classifiers you want to flag, right? So at the beginning, we're going to initialize every sample weight to be 1 over m, where m is the size of training data, right? So we're going to run big T iterations. Inside each iteration, we're going to find a classifier HT whose weighted classification error is better than 0.5, right? That's random guess, right? Then we compute the vote for this classifier HT following this formula. Right? And we use this vote to update the values of the weights for every training example following this. Right? Again, I want to emphasize again how to compute ZT. You can just put it aside, just multiply each previous weight DTI with this exponential factor, and then add up all them together, get ZT. Then you're gonna guarantee that your summation of the newly updated weights are 1, right? So this is very important. If you don't do this, right? If you don't make sure that your summation of the sample weights is 1, then you will have some problem in running our algorithm, right? It will exhibit weird behaviors. So just be careful. So then we finish iteration T, right? We'll proceed to iteration T plus 1, and now we find a classifier again, right? And then calculate the vote and update the weights of training examples. We do that again until we finish all big T iterations. And then at final step, we return a sample hypothesis by linear combination of every weight classifier, right, according to its vote. And the question regarding these algorithm steps, right? And we're gonna implement your ADA boost algorithm. You're gonna implement your ADA boost algorithm following this algorithm framework, right? Just to make sure every step is clear.
So the only stopping condition is just if we reach out to negative 18.
Yes, yes. Yeah, I mean, you can add more stopping conditions. Like here, we just gave a general algorithm framework. Any other question? You just equally weight every example at the beginning. Any other question? Okay, great. So now back to our toy example, right? Suppose we follow the ADA boosting procedure, right? We got these three hypotheses, right? And we got their votes, and we want to look at our final hypothesis, right? What does it look like, right? It look like this. This is our new classification boundaries. So you can see that it gives you a very complicated classification boundary with zero training error, right? So this is just to showcase that the boosting algorithm can return you a very powerful hypothesis. Okay. Depends on how we initialize. Yeah, but this I guess I should explain it that way, right? Actually, the final hypothesis will be dependent on how many classifiers you're going to use, right? Initially, okay, you set all the weights are to be the same, right? You run your weight classifier, it will always be H1, right? And then you do sample weight adjustment, and you rerun your weight classifier. You got H2, you got H3 accordingly. You can keep running that, right? Of course, if you run 10 iterations, right? You got 10 classifiers, you assemble them together, it'll give you even more complicated classification boundary. But here is just to showcase like 3 weight classifiers are enough to give you zero training error. Another question? Okay. So now let us think about a more specific question, right? So ADA boost is often combined with decision trees. Right? So what kind of weight classifiers can we use? We can construct a very shallow decision tree as a weight classifier. Right? For example, I can use decision stump, meaning that I only expand the tree for one level. Every time I just choose one feature, one attribute to split data, and then I grow a bunch of leaf nodes. That's it. Right? Then there's a question, right? When you are asked to implement a decision tree based boosting algorithm, right? We must make sure that our decision tree, our ID3 algorithm, can run on the weighted training set, right? How can we do that? How can we do that? What's the key step of ID3 algorithm? Yeah, splitting using A, right? But how do we pick up A? Information gain, right? Then the question is, how do we compute the information gain for the weighted examples, right? How to do that? Yes, right? Right now we connect back to our fractional counts, right? Right. That's why we emphasize that a little bit complicated method to complete to complete missing features, right? So because the same strategy, same computational technique will be applied here, right? After we weight those examples, right, we actually can view the training set as fractional examples. Now, when we compute the information gain, we just shove the weights into the computation, and that's it. You follow exactly the same procedure when you compute the fractional examples, when you do the splitting, all kinds of stuff. Right? That's why in our homework 1, you were asked to do that. Right? Here, I want to give a more concrete example. Right? So, suppose this is like 5 examples or just our training set, right? So we got run 1, meaning that for every example, we'll assign the same weight, which is 1/5, right? 1 over 5, because we have 5 examples, right? And when we compute information gain, suppose we are only doing like based on entropy, right? So that means to compute the entropy, we need to calculate P positive, P negative, right? P positive is just the proportion of positive examples. It's just 3 over 5, right? You got 3 examples, right? But you need to add up their weights together, which is 1 over 5 plus 1 over 5 plus 1 over 5 is 3 over 5, right? And similarly, you can compute P negative is 2 over 5. Does it make sense? Right? And you just shove your P plus P negative to the formula, to the entropy formula, right? You got entropy. And similarly, when you do the splitting, you're gonna partition those examples into different subsets, and you count the total fractional examples in positive, negative, and compute the entropy and so on. Okay. And here I give another example, right? Suppose in round 2, we readjust the weights of the training examples, right? D2, right? It turns out that the weight for the first examples is 2 over 8. Second example is 1 over 8. 3, 4, 5, their weights are 1 over 8, 3 over 8, and 4 1 over 8. So now what is P positive? Excuse me? 5/8, right? How do you compute that? Add them together, right? So, and P negative, you just add up the weights for the negative examples, which is 3 over 8, right? We compute entropy. They're just be very careful, right? If you don't implement the weighted, the correct implementation, if you don't have the correct implementation of those weighted examples, then your ADA boost will perform very badly, right? It won't work. Right? So just want to make sure that you guys are very careful and very clear about this step. Okay. I want to give a little bit theoretical results for the ADA boost learning algorithm, which can show you like how powerful it is. Right? So here's the theorem. Suppose we run the ADA boost algorithm for big T iterations, and we denote the weighted error epsilon t by half subtracted by gamma t. So remember, epsilon t, we need to make sure that okay, our weight classifier is slightly better than the strong than the half, right? So that's why we can represent our weighted error by half subtracted by some positive number, gamma t, right? So here we make assumption, right? That is, gamma t has some lower bound, some positive lower bound gamma, right? Non-zero lower bound gamma. If that's the case, then we can show that the training error of your final hypothesis after big T iterations will be no less than this guy. Well, no less than e to the power of -2 gamma squared times t. What does it expect? What does it reflect? What? Yeah, it's upper bound. It's not upper bound for generalization error. It's just upper bound for the training error. Right? So what does this result reflect? Right? What can we observe from that? Yeah, it goes down. It goes down very, very fast, right? Right, it's the exponential bond, right? If you increase, and gamma square is a constant, right? Maybe it's small, but it's just constant, right? And when you increase t, you can see that the training error decreases exponentially fast. It shows that actually the AdaBoost algorithm itself, right, is gonna provide you a very strong classifier. It can quickly fit the training data very well, right, along with the increase of training iterations. And here I just want to emphasize that this assumption is kind of like optimistic in practice, right? It's not. It does not always the case in practice, right? But anyway, it doesn't matter, right? We just want to showcase that. Okay, if these assumptions are hold, right, your training error can decrease very, very fast. So we want to release the proof. Proof is relatively simple. We'll release it on. We'll release the proof in our course website after our lecture. If you're interested, you can take a look at that. It's just a simple statistics and simple equality inequality tricks. So what does this theorem further reflect, right? As long as we can run enough number of iterations, we can perfectly fit the training data, right? I mean, of course, we need to assume that this this lower bound assumption is hold, right? But if this lower bound does exist, then you can imagine that we can train our AdaBoost classifier with zero training error eventually. Then a natural question will be, okay, it can so easily overfit the training data. Well, will it make our generalization performance worse? Yeah. So there's some kind of like very interesting observation is that even you got zero training error for AdaBoost, in many, many practical applications, it doesn't leave your generalization error or test error. Right? So this is the typical behaviors of the variance of the training error, right? Run some decision trees, decision stumps on some like a large data set. So you can see that along with number of iterations, the training error goes down very fast, right? And this is just individual classification errors, right? You can see that actually the weighted error are not guaranteed to be decreased as well. It's often like perturbate, sometimes even kind of increase. Right? The reason is that along with the training, right, you can see that those are largely weighted examples. There are those examples that are hard. Right? So you keep running your weight classifiers. The weight classifiers, they have their limited capacity. It will make them harder to correctly classify those difficult examples. That's why typically you will the weighted error is not like drops quickly. It actually is kind of perturbating. However, when you look at test error, right? So in our intuition that okay, typically it will be like this, right? When you run along with the iterations, right, your training error goes down smoothly, right? But at some turning point, your test error is gonna level up because you kind of overfitting the training data. You're gonna be misled by the noises or errors in your data. So you should have a worse test performance or generalization performance, right? This is actually constantly observed in numerous other machine learning models. However, for AdaBoost, it doesn't look like it. So here the blue line still represents the training error, but the red line actually is the test error or generalization. So you can see that although after just the 10 more, well, I guess it's 12 or 11 iterations, yeah, training errors has already reached down to 0, right? And you keep running that, you just have a constant 0 training error, right? But your test error actually does not jump up. You just keep doing it. Right? And you can see that slowly, it kind of even slowly going down. And actually in your homework, right, our coming homework, when you test your AdaBoost algorithm on the real data set we provided, you're gonna observe similar performance, similar behavior. Although, because in our test data set, number of features is small, the size is not very large, so the training error, it's not necessarily like you're gonna observe zero training error, although the training error has already been very small, right? But you will see like similar behavior. That means error, even when it reaches minimum, your test error won't go up. So this is a strange observation, right? Test error may decrease even after training error has hit zero. Why? This is an open question, and Robert Shapiro and his collaborators have provided some possible explanation, but this is still kind of open question. Okay, so today we have introduced the AdaBoost algorithm, one of the most popular boosting algorithm. It's very, very successful, very widely used, very classical, right? What is good about AdaBoost, right? It's simple, fast, and there's only one additional hyperparameter to tune. That's big T, right? How many weak classifiers do you want, right? And you can combine it with any weak learning algorithm, right? Which means that we're only to look for classifiers that's slightly better than chance. Right? But there are some also some kind of defaults, right? Key values. So the performance often depends on data set and also the choice of weak learners, right? And if your weak learners are too complex, meaning that like 20 level decision trees, it might fail. Right? So that means your weak learners must be appropriate, right? It cannot be too fail, it can be too weak, and it cannot be too complex. So there's a kind of like trade-off. So empirical evidence shows that if you use your AdaBoost with decision stumps, that means only one level of decision trees, right? It is practically the best approach to try if your number of features is small, no more than hundreds. Right? This is just our practical experience. Right? Okay, yeah, let's stop our discussion today. Right. Next Tuesday, I will be traveling to the National Science Foundation. I have to join their PI meeting. So the class in next Tuesday will be canceled. I will release the announcement on cameras later. And see you next week.